Topic 11, Measurement and Data Processing. 11.1, Uncertainties and Errors in Measurements and Results. Quantitative data in science. Qualitative data are the non-numerical data. This includes the all chemical or physical information obtained from observation, not from the measurement. So task 1, identify the qualitative data from the video burning magnesium in air. So if you look at this video, you can see that the magnesium, when the magnesium burns in air, it produces a white, bright light. Okay. Quantitative data in science. Quantitative data or numerical data, this would normally be anything that is measurable. So if you look at this titration video, the teacher in this video is doing a exam-based titration. So when we do titration, we always record the amount of the exam base we use during the titration, and these amounts, the numbers, right, are considered as quantitative data. Uncertainty in science. All measurements have some degree of uncertainty, and if you study physics, biochemistry, you always have to consider the uncertainty of your measurements, okay? So in IB chemistry class, we report a measurement by recording all the certain digits with its uncertainties using correct number of the significant figures. So let's go into accuracy versus precision. Accuracy is how close a value is to its true value or theoretical value. Okay, precision is how repeatable a measurement is among several measurements of the experimental values. So let's talk about this using the bull's eye over here. So if you look at the first bull's eye, you can see that all the data points are right in the middle. So it means it's highly accurate and highly precise, okay? And if you look at second bull's eye, you can see that the data values is not really in the center, but they are actually all close together. Means these data values are highly precise, but it's not accurate, okay? Because it's not close to theoretical value. If you look at the third bull's eye, the values are actually like kind of all everywhere, right? But they're close to the theoretical value or the middle of the bull's eye. So we can say these values are accurate, but they are not precise because they're not close to each other. And if you look at the last bull's eye, they're not accurate, right? The data is like everywhere and they're not close to the middle. They're not close to theoretical value, right? So they are not accurate, and since they're not all close to each other, they are not precise too. Experimental errors in the measurement. Every single measurement has a degree of uncertainty associated with it. This is termed the experimental error. And the two types of the experimental error are random errors and systemic errors, okay? So let's go into random errors first. Random errors are completely random. That means it causes a one measurement to differ slightly from the next and comes from the unpredictable changes during the experiment, okay? So when you have a random errors, your data is not accurate and not precise, or your data can be accurate but not precise, okay? So what causes the random error? It can arise due to the limitation of the measuring apparatus, okay? And also, random errors cannot be eliminated, but it can be reduced by the repeated measurement, and random errors affect the precision of the result, okay? So random errors have an equal probability of being high or low as compared to the true value, and it occurs in estimating the value of the last digit of a measurement. So how to calculate the random errors? I just said it, right? But let's go more deeper into it. So for the analog measurement, random errors can be estimated to be half of the smallest division on the scale. If you have a digital reading, such as electronic balance, random error of the positive minus smallest division. So if you look at this one, okay, we have a beaker over here. So it has like 10 markings, okay? No, actually it has 20 markings. So the random errors will be 20 divided by 2, right? So your random error for this beaker will be positive minus 10. Okay, and for this one, the digital reading, which we have electronic balance. In this case, the smallest division is 0.00. Okay, so that's smallest decimal point, right? So our reading will be plus minus and 0.01. This will be the uncertainty for this electronic balance. So practice. Let's do another practice. Here, so we have a ruler and I like to identify the length of the blue bar. So I can see that like the blue bar kind of stops at 31, okay? It can be different for you, but for me, I think it stops at 31. So what is the length of the blue bar? It's 31, but since we are in chemistry class, we have to report the data with the uncertainty. So my case, so I think the measurement is 31, and also since I include uncertainty, we have to calculate it, right? So we have analog measurement tool here. So we take the smallest division, which is 0.1, not 0.1, right? Smallest division in this case is 1. So we take smallest division 1 and divide by 2. So means we have 0.5 as our random error, means uncertainty. So my data for this case will be 31.0 centimeter plus minus 0.5 centimeter. Okay, so examples of the random errors. Random errors can caused by the air bubbles in reagent. It makes the reading wrong, right? And improperly mixed reagent, reagent lines, sampling or reagent syringes, improperly fitting pipette tips, clogged or imprecise pipette, and fluctuations in power supply. So, and random errors have an equal probability of being high or low as they compare to the true value, and it occurs in estimating the value of the last digit of the measurement. Let's talk about the systemic errors. Systemic errors are always either constant or related to the actual value of the measured quantity, or even to the value of a different quantity. Okay, so when you have system errors, you can have data that's not accurate either, but precise. Okay, means the data values are close to each other. And also you can have accurate and precise data. So when you have like accurate and precise data, that means there's no errors, right? No systemic errors. And also, like I already told you that repeated trials and measurement will reduce the random errors, but systemic errors cannot be reduced. Okay, once you have systemic errors, you have it. You cannot really fix it. Okay. So systemic errors are always either constant or related to actual values of measured quantity, or even to the value of a different quantity. So there are 3 types of the systemic errors. They are observational errors, environmental errors, and instrumental errors. And what causes the systemic errors? The observation error. So when you made some observation wrong, right? And errors due to the instrument, okay? When you set up your instrument wrong, and errors due to the wrong assumption when you started with the wrong prediction or assumption about your experiment. So examples of the systemic errors. When you have a leaking gas syringe, it can cause the systemic error. When you have a calibration errors in pH meters, okay, it can cause the systemic errors. When we have a calibration of the balance wrong, you can cause it. And also when we have a liquid evaporating, okay, and if it changes the data or the measured, the final volume, it can cause the systemic errors.